In today's session, we look at one more data structure which is extremely useful in storing information. Until now, we had seen linear data structures which were stacks, linked lists and queues, and we looked at nonlinear data structures. We looked at two applications, mainly the sorting application and the searching applications. For searching applications, we used both linear and non-linear data structures. Linear structures were used for when searching was done with hash tables. Non-linear data structures was done when searching was performed with the binary search trees or the AVL trees or the 2-4 trees. So, we look at the data structure graph. So, graph is basically a pair of two sets VE, where V is called a set of vertices and E is the set of edges connecting the vertices of V. E is also thought as of a relationship between the vertices V. So, given any set V, E specifies the relationship between the elements of V. A graph can be visually represented as this. In this particular case, we have got 5 vertices of A, B, C, D, E, and we also know what are the edges. So, A, B is an edge, A, C is an edge, C, E is an edge, C, D is an edge. Similarly, we know D, E is also an edge. This particular example also can represent a real life situation. A, B, C, D, E could be just 5 persons in a particular room or 5 persons that you want to look at or consider, and the set E, which is the set of edges, can be the relationship between these 5 people. Right? It can happen that A, B, C, D, E we say or A is related to B if A and B are siblings. So, sibling is a relation. So, you can define A is going to be related to B if A and B are sibling, or your relationship can be something else. It can be A and B are friends. So, instead of say A and B siblings, I can say A is related to B if A and B are friends, or it could be any other relation, or A and B have taken a same course in a college. If you are looking at, if A, B, C, D, E happen to be 5 students in a class, we will say A is related to B if they have taken a particular, they have a course in common. So, set E can represent real life relationships between individuals, or we will see it can be used to model lot of real life applications. So, a graph is a pair of two sets V and E, where V is a set of vertices, E is a set of edges connecting the vertices in E. So, if I look at E, so E is actually, if you look at the way E is defined, it is a subset of the Cartesian product of V with itself. So, it is a subset of V cross V. Right? Element of E is a pair A B or whatever. So, where A belongs to V and B also belongs to V. So, you can visualize either algebraically as a graph as a pair VE, or one can use a diagram to represent a graph. Most of the time we will be using the visualization rather than the algebraic definition. The visual representation helps in better understanding of the ideas that we intend to work with. So, in practice we will never identify graph as a set VE with what is V, what is E. We will just look at graph as something like this, and then if required, we can write down the set V and set E, right. So, if you given a visual representation, you can easily write down what is V and what is E. So, most of the time we are going to use the visual representation of the graph. So, a graph, as you said, is going to be used extensively in modeling of real life problems. So, in this particular example, a vertex is going to represent an airport, and we are going to store whatever a 3 code letter, which is going to be the airport code. An edge is going to present whether there is a flight between 2 airports. So, the relationship that we are having between 2 cities or 2 airports is whether there is a flight from this airport to the other airport. In the visual representation, that is represented by a line joining the 2 vertices or 2 nodes. So, your vertices are this, and a line represent that there is a route between, or the edge represent that there is a route between the 2 vertices. We also use an idea of what is called a weighted graph. That means the edge has a weight. The weight is, in this case, the distance between the 2 routes or distance between the 2 airports. It could be weight, could be even the cost of the ticket, or it could be the time, or it could be anything else. So, a graph will have vertices, edges which are going to connect the vertices. It can also, edge can also have a weight, in which case we will call it as a weighted graph, and that weight will indicate some numeric value that is going to specify the distance or the time, or if it is a network, it can be the bandwidth or a quality of that particular edge. Another example where we are looking at a set of few people and a relationship between these 2 people. So, we say that 2 people are related if x is younger than y. So, if x is younger than y, we say x is related to y, or we will say there is an edge between x and y. So, if you look at the graph, it is represented as this. So, we are not writing down. If you want to write down the algebraic expression, you have to write down. So, your V will have 6 people, and the number of edges you will have is going to be quite large. So, it is going to be, and it is not very easy to draw inferences from the algebraic definitions. Whereas, the visual representation, it is easy to see that there is an edge from John to Mary, then John is younger than Mary, right. So, you see that there is an edge from John to Mary, that would mean John is younger than Mary, and so forth. Similarly, John is younger than Tom, and John is also younger than Helen, and whatever. So, the ages, so the representation helps in easily interpreting the relations that the individuals share amongst each other. If you look at this example and the earlier example, there is a subtle difference. If you look at this particular example, we see that in this example there are no arrows for the edges. That means, if you have a route from city A to city B, then you also have a route from city B to city A, or airport B to airport A. So, this relationship is called a symmetric relationship. That is, if A is related to B, then B is also related to A, and this happens in this particular example. If you have a path from A to B, then you have a path from B to A. So, in this case, we have a edge which has no direction to it, or which has no arrows to it. Now, whereas in the other example, your relationship is not symmetric. That is, if x is younger than y, then y is not younger than x. That means, if x is related to y, then y is not related to x. So, the relationship that we are trying to catch in this particular example is a non-symmetric relationship. So, in this case we represent this non-symmetricness by using what are called arrows instead of edges without arrows. So, we have here, as you see, an edge which is directed, or an edge with an arrow towards Mary, or we have a edge from John to Helen with an arrow. Such a edge would mean John is related to Helen, but Helen is not related to John, because the relationship by which they are related is not a symmetric relation. So, whether your graph will have edges with arrows or without arrows is decided by what relationship is defined on the individual vertices or elements of that particular set on which you are trying to look at the relationship. As we already seen examples, there are plenty of applications. A lot of real life problems can be modeled as graph. So, you can model electronic circuits as a graph. Transportation networks can be modeled as a graph. We already just saw an example of a transportation network, where you have cities as your nodes, and if you have a route between two cities, or a flight or a train connection, that would be represented by edges. You can represent computer network using graphs, where your desktops or machines are going to be vertices, and if they are going to be on a LAN or going to be connected to each other, that is going to be represented by an edge. So, lot of real life applications are going to be modeled as a graph, and so there are plenty of real life problems that are based on these applications, which are going to be solved once these problems are modeled as graphs, and we try to understand the solutions using the graphs. As already observed, your graph there can be two types. One where it represents relationships which are symmetric, and the other where it represents relationships which are not symmetric. So, we define this in terms of directed edges and undirected edge. So, directed edge means it is an ordered pair in which the order is going to be important. So, when we write u v, this means it is a directed edge from u to v. We call the first vertex as the origin vertex and the second vertex as the destination. So, you also called source or destination, or origin and destination. Usually flight networks are directed graphs. We know from our experience that there can be a flight from a city A to city B, but the same operator may not run a flight from city B to city A back. So, typically flight networks are represented using directed edges. Undirected edges, in which the order of the vertices is not going to matter. So, you have a pair u v where it is not important whether u is going to be written first or v is going to be written first. So, in a directed edge, u v is different from v u. So, in a directed edge, u v and v u are going to have a different meaning, whereas in an undirected edge, u v and v u are going to mean the same, because in an undirected edge the order does not matter. So, many times this is also to avoid confusion, a set notation is used for showing this. So, instead of writing round brackets, you use curly brackets. So, either you can say it is an undirected edge and understand that u v is an unordered pair, or represent it as a with the set notation and put them in curly brackets. By convention, we will not use the curly brackets, but whenever we mean an edge is undirected, we will represent it as u v with understanding that it is an unordered pair. Depending upon whether your graph has edges which are directed or undirected, you define a directed graph and an undirected graph. So, directed graph is going to be a graph in which all the edges are going to be directed, and an undirected graph all the edges are going to be undirected. Some more terminology. If you have a edge V0, V1 in an undirected graph, we say V0 and V1 are adjacent to each other. So, adjacency relationship in an undirected graph will be a symmetric relationship, whereas in a directed graph it is not going to be a symmetric relationship. So, if V0, V1 is an edge in a directed graph, V0 is adjacent to Vi and Vi is adjacent from V0. So, we do not say Vi is adjacent to V0, whereas in an undirected graph V0 and Vi both are adjacent to each other. So, we use this adjacency relationship quite often. So, if one has to travel in a graph, you can only move to a node or to a vertex which is adjacent to the source vertex. So, adjacency is going to be an important relationship that we are going to use. We are going to still use a few more notations and terminologies. For us, a degree of a vertex is the number of edges incident to that vertex. So, for a directed graph where adjacency is not a symmetric relationship, we have two notions, an in degree and out degree. In degree, as it means in English, is the number of edges that have V as the head or which is directly going into V. Out degree are the edges which are directed outside V or away from V, or which has V as the tail. So, in a undirected graph, it is just the number of edges that are incident on V. For a directed graph, we have in degree and out degree, and your degree is the sum of the in degree and the out degree. It is very easy to prove that if di is the degree of vertex I in a graph G with n vertices and E edges, then E is going to be sum of all the degrees divided by 2. You are going to divide by 2 because you are going to count an edge twice. So, an edge which is incident on a vertex is going to be counted twice. So, for example, if you have an edge from say U to V, you are going to count this edge when you are going to count degree of U, and this edge will be also counted when you are looking at degree of V. So, an edge is going to be counted twice. So, the number of edges is going to be the sum of the degrees divided by 2. It is a simple but important result that we are going to use. These are some examples of in degrees and out degrees. So, you have a example of so G1 and G2 are examples of undirected graphs, whereas G3 is a directed graph. For each vertex, we have written its degree. So, 0 has 3 edges incident on it. So, degree of 0 is 3. Similarly, degree of 1 is 3, degree of 2 is also 3, and degree of node 3 is also 3. This is a graph which we have already seen. It is a special type of graph which is called as a tree, and we have already looked at definitions in trees. So, if you look at this node has 2 edges incident on it. So, its degree is 2, whereas this node has this and this edges incident on it. So, its degree is 3. Similarly, this degree is 3 and all the nodes at the last stage or the last level have degree 1. Let us look at an example of a directed graph. So, this is a directed graph. So, if you look at 0, it is in degree. So, that is the number of edges which are headed into 0 is only 1, whereas out degree is also 1 because there is only one edge which is going out of 0. Now, let us look at 1. In 1 there is only a single, there is a single arrow which is going out of 1. So, it is there is a single arrow which is coming inside 1. So, in degree is 1, whereas there are 2 arrows which are going out of 1. Therefore, its out degree is 2. Similarly, for 2, its in degree is 1 and there is no edge which is going away from 2. Therefore, its out degree is 0. So, for an edge you can have in degrees and out degrees also 0. So, for example, if you have a directed graph like this and a vertex like this which is away from the or which is isolated from the main graph, then for this vertex its degree is 0. It is because its in degree as well as out degrees both are 0, that is there are no edges which are leaving from this node and neither there are any edges which are directed inside this node. So, in general a degree of a vertex can be 0. In that case, that vertex is away from all the other vertices or is not connected to any other vertices. So, it is like in a group of 10 people, if your relationship is friendship, then there is a person who is not a friend to any one of this other 9. Then in such a visual representation, this node representing this particular individual is going to be not connected by an edge to any other node. We want to use a few more terminology. So, we are going to say a path is going to be sequence of alternating vertices and edges, or sometimes we will only write sequences of vertices. So, a path, for example, in this graph is going to be like this. So, this is going to be a path which is alternating sequence of vertices and edges. So, V, then you take via B go to X, via H go to Z. So, this particular P1 is represented by this path. We can also represent this by just writing V, X and Z. So, either we use this alternating notion of vertex edge vertex, or simply write down a sequence of vertex such that Vx is an edge and Xz is an edge. So, rather than writing a sequence of alternating vertices and edges, we can only write a sequence of vertices in which if I take any consecutive vertices or nodes, then that would represent an edge in the graph. A simple path is such that in all the vertices and edges are going to be distinct. So, if you look at P1, you see that no vertex or edge is repeated. So, it is called a simple path. Whereas, if you look at P2, it is from U, it takes C, goes to W, takes E, goes to X, takes G, goes to Y, and from Y it takes F and comes to W. So, this W vertex is repeated in the path. Such a path is not a simple path. So, path can be simple or can be not simple path. Path can be thought even as if this particular graph is representing a map of a city, then that means if I have two vertices, any 2 points in the city, there is a road connecting these two cities. So, we will see that graph are used a lot in modeling real life applications, and solutions to them can be achieved via solutions to graphs. We have special type of paths which are called cycles. So, in a cycle, your source and destination is going to be the same point, that is you where you start, you come back to there. So, in this particular case, if you take V, go to X, go to Y, W, U and back to V. So, you have a path in which your source is actually equal to destination. So, a path in which your source is equal to destination we will say is a cycle. Similarly, as in path, you have a simple cycle and just a cycle. In a simple cycle, all your vertices and edges are going to be distinct. So, this particular example of a cycle is a simple cycle, whereas if you look at a cycle like this, so you start from U, go to W, go to X, go to Y and go back to W. So, you are going to again come back to W. So, in this cycle, and a vertex W is visited twice, we will say such a cycle is not a simple cycle. So, cycles are like paths, are there specific type of particular type of paths, and you have cycles and simple cycles, like you have paths and simple paths. Some simple properties. Property 1 we have already seen, that if you look at the sum of the degrees of all vertices, you get twice the number of edges. M here is number of edges. In a property 2, in an undirected graph with no self loops and no multiple edges, M is less than or equal to n into n minus 1 by 2, that is the number of edges you can have at most is n into n minus 1 by 2. This because each vertex has degree at most n minus 1. Right. If I have 4 vertices, then each degree can have at the most n minus 1 neighbors. Right. For example, in this case, this has degree 3, this has degree 3, this has degree 3, this has degree 3, and so the number of edges in this case is precisely going to be equal to 6. Or this also means that the maximum number of edges in an undirected graph without self loops and multiple edges is n into n minus 1 by 2. So, each vertex has degree at most n and there are n such vertex. So, you will have n into n minus 1 by 2. So, that is the maximum number of edges that you can have on a in a undirected graph without self loops. Such graphs are also called complete graphs. This is called a complete graph on 4 vertices. So, graph is complete if if a node is connected to all the other nodes. You have also what are called connected graphs. So, in connected graphs, given any 2 vertices, they are connected by some path. In not connected or disconnected graphs, you will have vertices which are not connected by path. So, if I take this as vertex A and this as vertex B, then there is no path from A to B, whereas if I take this as A and this as B, then there is a path from A to B. In fact, in a graph there can be many paths from a vertex A to B. Connected would mean there is at least one path. A subgraph is just a subset of vertices and edges forming a graph. So, given a graph, you take a subset of vertices and the edges corresponding edges, that becomes a subgraph. And you also have a graph which is not connected, we have what are called connected components. So, if I look at this as a complete graph, it has 3 connected components. Each component, say C1, C2 and C3, is itself a connected graph. This, if I look at this graph, this has 2 connected components. So, you have connected subgraph and you have what are called connected components. These are just some examples of subgraphs. So, if I look at this particular graph G1, if I just take this one vertex, this is sort of a trivial subgraph. You can just take this part, this becomes a subgraph. You can just take the part below, this also is a subgraph. Similarly, this also is a subgraph. So, subgraph is something that you should be able to fit into the main graph. Right. So, this itself can be identified as it is in this graph. Similarly, you can do this for a directed graph. So, this G3 is a directed graph. So, this is a subgraph, whereas this is a subgraph and so forth. As we have seen, trees are special types of graphs. Each node has 0 or more child. Important is a tree is a connected graph which is acyclic. If you recollect, a tree, for example, a binary tree, we had represented like this. Now, we see that a tree is connected. That means, if I take any 2 nodes in a tree, say this node and this node, then there is a path from between these 2 nodes. So, this is a connected graph. We also see that in a tree there are no cycles. Therefore, a tree is a connected acyclic graph. So, any connected acyclic graph is a tree. If you have a collection of trees, we will say if my graph is all this put together, so it is a collection of trees, we call it as a forest. After understanding graphs, it is crucial to understand how we are going to represent such graphs in our machines. If we want to model real life problems in graphs and work with them, then we should be able to represent it in the machines. So, this usually has 2 approaches, one is called adjacency matrix and the other is called adjacency list. So, in an adjacency matrix, we represent it by a 2-dimensional array or a matrix in which ijth entry is 1 if Vi and Vj are adjacent, and ijth entry is 0 if there is no such edge. So, a graph can be represented as a matrix or a 2-dimensional array of size n cross n. The ijth entry is 1 or 0 depending upon Vi, Vj are adjacent or not. It is very simple to observe that adjacency matrix of an undirected graph are symmetric, whereas for a directed graph they need not be symmetric. So, these are examples of adjacency matrices. So, we have a graph G1 and we have the adjacency matrix of G1. So, 0 is related to 1. So, this 1 is here. So, typically we can write V vertices as this 0, 1, 2, 3, 0, 1, 2, 3. Now, since there is no self loop at 0, that is we do not have a self loop at 0, this entry is 0. Now, 0, 1 has an edge, so there is 1 here, 0 to 2 is an edge, so it is here, 0 to 3 is an edge, so it is here. Similarly, for 1, 1 to 0 is an edge and so forth. So, if I look at any ijth entry, so if I am looking at this, this indicates whether V1 and V3 are connected or not, and they are connected. So, 1 indicates V1 and V3, or node 1 is connected to node 3 by an edge. We see that this is a symmetric graph, whereas this is an adjacency matrix representing a directed graph. So, this is not a symmetric matrix. So, for example, there is a, if I am looking at this particular entry, this means 1 and 2 nodes are connected by an edge, which is here. But if you look at entry 2 1, it is 0, that means there is no edge from 2 to 1. So, it is a not symmetric matrix. So, you can represent a graph using as a 2-dimensional array. There are lot of merits using adjacency matrix notation. Easy to implement. You can easily determine the connections of vertices, or if there is an edge between two vertices. If you want V and Vj, simply go to the ijth entry of your matrix, check 1 or 0. So, within a constant time, that is, since it is an 2-dimensional array, we know it is going to be a direct axis. So, axis is going to be in one step. So, in one step we can decide whether Vi is connected to Vj or not. The negative part is, whatever your graph is, the space required is going to be of order n squared. That is, I can, if I have a graph with lot of vertices, but small number of edges, then we are going to require n squared memory to represent this, and in this n squared memory lot of entries are going to be 0. So, the merit is easy to implement, easy to interpret, but it is inefficient in terms of memory requirement. That is, you whatever your graph is, small, large, when we say small or large, we are looking at number of edges and number of vertices and number of edges. So, if you have large number of vertices, small number of edges, then using adjacency matrix, we are going to make use of lot of extra memory, which may not be needed. So, we have another representation in this case, which is called adjacency list. So, it is represented by a 1-dimensional array of linked lists, where Li is a linked list containing all the nodes which are adjacent to node I. The nodes of Li are not in any particular order. One can use a convention to make it uniform, but as such it may not be any particular order. So, this is an example of a adjacency list. So, 0, 1, 3. So, this is an example of a undirected graph. When we will have to write down examples for directed graphs also. So, we see 0 is adjacent to 1, 3 and 2. So, at 0 we maintain a linked list, which will have all nodes which are going to be adjacent to 0. So, 1, 2, 3 are adjacent, whereas if I look at 3, it is adjacent to 1 and 2 or 0. So, in this case every node is adjacent to the other node, except if I look at 1, at 1 it is adjacent to 0 and 2. There is a mistake here. This is wrong, that is a typo. 2 is not adjacent to 1. So, that is a typo here also. There are 2 typos here, sorry for that. So, in the linked list which is at 1, we will have only entries 0 and 3, and 3 at 2 there will be entries only 3 and 1. So, at 1 we will have only 0 and 3, we will have only 0 and 3. Similarly, at 2 you will have only 3 and 0. So, this is called an adjacency list representation. In this graph 2 is not adjacent to anything. So, you have a null list here, or this list is going to be empty. So, you can use linked list structure to represent graphs using via adjacency list structure. The advantages is it uses less memory, less storage on your machine, because you are going to exactly have that many nodes as there are edges in your graph. The flip side is to interpret it takes time, right. So, if you want to check whether two particular nodes are connected or not, one has to go to the linked list at that particular slot and check whether adjacency relationship is there or not, right. For example, in the preceding example, if you want to check whether 0 and 3 are adjacent, adjacency matrix would have taken only one step. Here one has to traverse this linked list and see that 3 is there in the list to say that 0 and 3 are adjacent, and we know traversal in a linked list is sequential. So, you have to start from head and go probably all the way to the end in the worst case. So, it is inefficient in terms of interpreting or recovering information from the structure. Thank you.